Good morning, everyone. Come on in. A couple minutes left. There's only three of you here. I'm getting my
How you
notes
do?
ready.
How you doing?
Not too bad. Still don't think I'm necessarily better, but I'm going to try to press through classes and then slip out to a doctor if possible.
You haven't seen a doctor yet?
No, I mean, some time ago, the first time I had one, I saw them and they sort of told me to expect it.
Yeah, I thought I remember us talking about for some reason kidney stones earlier on. And it was like a couple weeks ago.
Yeah,
I
exactly.
don't
Yeah, that's the
know.
excitement of an old person's life.
Oh man.
You talk
Yeah, I
about
hope he.
something health wise and then it comes true next week.
What are we living in a nursing home?
Yeah, that's right behind that curtain there. Uh, so yeah, my wife is the one that's convinced it's a kidney stone. I'm not doubting her necessarily, but I just know that my kidney stones were never painful, and now they are. So
Oh my God. Yeah, they're never enjoyable.
no, yeah, before it was like I passed them, but I didn't even know until I saw blood or something. But now it's like, oh, you're gonna have a kidney stone, and it's gonna hurt, and you're gonna
Yeah.
whine about it and feel sick and everything else.
I mean, out of curiosity, I mean, is it just the pain?
Yeah, it
Like,
started as just a back pain. I had
oh,
I
back
was
pain.
working on putting some furniture together day before, no, Thanksgiving Day, and something pulled in my lower back, which I have chronic back problems anyways. I broke my back in '98, so I've always had those problems. Uh, but it just didn't go away, and in fact, it got worse. And then finally, it started to protrude, like the back pain shot all the way through my body to my front side,
Oh,
through my stomach, and then down lower too, like below my belt line. I was like, "Ah, man, this sucks."
oh my gosh.
And then I
Mm.
just noticed that I can't urinate anymore. So yay!
Oh, okay. All right.
So
That's a
that's
pretty
where the
big
excitement
symptom.
comes. Yeah, that last symptom probably is a teller.
Yeah.
Think she might be
Oof.
right on that one.
Uh,
Oh, so yeah, that's the nature of it. All right, I've made a file. Oops, wrong thing. I've made a file that we can keep our notes in today. And now I have to make a duplicate of it because you have to make a new file every time. Looks like that's good. All right, now we got all this. Well, it looks like I've got a pretty good number of folks in the class, so I want to go ahead and get started uh, with that. So one thing I want to tell you guys is I've decided on something else after you guys left class, talking to Hadim and Hussam and Guinevere and a couple other people. So I've basically decided that Monday, Tuesday, and Wednesday, well, for you guys, it'd be Monday and Tuesday, you're allowed to take the final exam. I'm going to send out some times of exactly when, but on Monday, that's the day you're supposed to take your exam. That would be supposedly happening for your class. On Monday, it would happen at noon. Uh, no, yeah, at noon. And for the 242 class, it would happen at 9:30 a.m. or excuse me, 9 a.m. So what I planned on doing is Monday, I know I'll have like 8:30 is a possibility, and then 9's another possibility, and then 10, and then 11, and then noon. So I'm thinking about having several hours on Monday that you can take it, and then again several hours on Tuesday that you can take it. And then my Tuesday, Wednesday class or my Tuesday, Thursday classes, they can access that Monday if they want to, but really their day is the Tuesday, and I'll have several specific hours they can start it then, as well as the same thing on Wednesday. So I'm going to have like a 3 day window, Monday, Tuesday, Wednesday. You're supposed to be Monday, Tuesday, but I could make arrangements if someone needs Wednesday at the absolute worst, but I'd probably need an excuse in that case. But you can definitely take to Monday. Instead of Monday, you can take it on Wednesday if you wanted. But like I said, I'll send out the times via email, and that'll all be done before the weekend so you can start making times. Uh, As I told you, basically any chapters beyond 10 are going to be extra credit, and I think I said beyond 10. And therefore, if you score a 70 or higher on chapter 11, chapter 12, 13, 14, 15, 16, whatever, if you score a 70 or higher on any of those, I'm going to go ahead and give you the full 100 for it as extra credit. If you take a 0 on 11 or any of those later ones, there'll be no harm to it. So basically, I'm capping out the homeworks at that last assignment. Additionally, here's the part I've been hinting at for you folks that were so worried about your low homework grades. Anybody that has a homework grade that's lower than their course average, I'm going to calculate their grade without the homework grade at all. But everything else will still be in the same proportions as best I can. But basically, I'll give you the higher score of the two scenarios: the scenario where I do the calculation as spelled out in the syllabus, and then the scenario where I completely ignore the homework and just take your online tests and face-to-face tests and lab. So that's the way I'm going to do the grading. That's why I told you guys to, focus hard on getting a 70, 75, but don't worry about any higher than that because there's some chance you might be fighting really hard to find the wrong answer because there are some mistakes, of course. So y'all can now, rest tight with regards to the homework. Don't tell anybody. This is something I do just about every semester because I like the homework systems that they have. They're really good and thorough, but sometimes they sort of miss the mark on what I'm shooting for, even though they have wonderful instructional problems that are able to walk you through more complex problems, even though those are the ones that students sort of hate. So, anyways, that's the two big announcements. Your test you can take on Monday, your test you can take on Tuesday, with some legal documentation of why you can't take it on Monday or Tuesday. I could possibly move it to Wednesday. And then again, my classes on Tuesday and Thursday, they can take it on Monday or, well, yeah, Monday, Tuesday, or Wednesday. And that'll be all of it. I appreciate that, Mike. Yeah, and a lot of this stuff that I'm sort of going over, I want you guys to use my YouTube channel to help you better understand the material because I'm doing a really quick version of chapters 14 and 15 today, just sort of skimming it, showing you the most important parts. What I need you guys to recognize from chapters 14 and 15 is the simple harmonic oscillator, the simple harmonic oscillator differential equation, the force harmonic oscillator differential equation, the damped harmonic oscillator equation, and the wave equations, and what those parts are, because that's stuff that just keeps on coming back over and over and over again. So we're gonna do a quick survey of chapters 14 and 15. And I'm still working on the final, making up a practice final for you guys. I'm not worried about it in terms of how long, because I know you guys are supposed to be working on your redo face-to-face tests. And as I instructed, you should do that first. Get all your redo uh, tests done. Then once you're done with that, then you should focus on taking the practice test. Okay. This will be a time, by the way, where you can ask questions about any problems you ran into on the face-to-face test or any past practice test or anything like that. But I just got to get through a little bit of material in chapters 14 and 15. We technically have literally from 9:30, which was supposed to be 9 a.m., but we have from 9:30 to 1:50 in principle. But I might discover that you guys don't have enough questions to keep me that long, and that's fine. Uh, I will have some more office hour opportunities, later today, later tonight, tomorrow, and tomorrow night as well. Then I could also possibly do something, if someone needs something on Friday or the weekend, I might even be able to cut out an hour of my time for you guys or a couple hours. So, anyways, let's go ahead and get started. Does anyone have any questions other than what I just stated? I know some of you came in late, so I might have to refer you to the beginning of the video so I don't have to repeat myself. Okay. Now,
Just a recap, hold on. Uh, the final exam is covering chapters, what chapters again?
oh, it will be chapters 1 through 11 and then 14 and 15.
Okay. All right.
Yep. Go ahead, ID. You just speak up, buddy.
I remember, so last time you said you were considering doing it or like probably gonna make it a partial credit test, so like not a multiple choice test. Are there made a final decision on that, or like when will we know?
Yeah, that's still very much a possibility. That's why I really want you guys to really take this opportunity to redo those face-to-face tests and really learn how to work them, because I'm leaning towards a smaller test that will be not multiple choice where you turn in your work, and you should, do the solutions more or less like they're explained in the redo test assignment. So hopefully y'all have all looked at that. But basically, you should have your problem and answers, and then below that will be your work. And I want you to start off with the word solution, and then as you need equations, I want you to write them up there by the solution, and then show yourself plugging the numbers with the units into those, at least in the initial step, and then solving said equations, and then clearly demarcating the very final answer with a circle or a box or something like that. So some of those rudimentary things, not working in circles, not working all around this way, not having floating mathematical symbols around, because those are really often indicative of someone who doesn't know what's going on. It generally looks bad when you see floating symbols in a problem. So I don't want y'all to do that, not because I'm biased against you, but because other people might be, and they're definitely going to take off a lot more points than normal if they see that kind of floating symbols around. So, if you're solving an equation, you need to have left side equals right side, next line left side equals right side, final line left side equals right side. Never is there just the left side floating around out there or the right side floating around out there without an equals. Okay. Uh, if you're thinking that way, then I get what you're doing, but you need to take time to put the rest of the equation on the other side. Uh, so yeah, by stating what principle you're using or stating what equations you're using, that tells me a lot right from the beginning, that you at least know what's going on, or that you don't know what's going on, or that you're trying a different way. And then I can fairly assess very straightforwardly, where math went wrong, as where you made a mathematical mistake as opposed to a physical mistake. And those points are very minor compared to making physics mistakes. Okay. So yeah, do prepare just in case for a face-to-face test that is online, but where you're going to type in an answer, or you're going to write in a solution and then write in an answer. All of that's fair game. And like I said, Hadi, you did miss this part. Uh, you will be allowed Monday or Tuesday to take that. And my Tuesday, Thursday classes will be allowed Monday, Tuesday, or Wednesday to take it. So, anybody else have any questions? Just for a roll, could each of you go ahead and chat me your first and last name? So everybody just type your first and last name in the chat, so I'll know who came. And it's just another roll day, so I'll have the roll for today. Thank you for that. Appreciate it, everybody.
Speaking of the test, sir, can we do it on paper, then give it to you instead of typing it on whatever
Yeah,
document that
if
you...
it's a handwritten one, that's probably the way it's going to be done. I probably
Oh,
won't
okay.
mess with a computer.
Yeah, because the computer is gonna take time.
Yeah, yeah, that's a little confusing, problematic, that sort of thing. So yeah, it would probably be, like I said, just a regular paper test, and we'd be best served by taking it, like in a bigger room or something like that.
Since it's going to be like multiple tests across multiple days, are the tests going to be like randomly generated from a bank, or are you going to make like individual tests?
Yeah, they're going to be somewhat different, but they'll also be somewhat similar. So if you happen to be one of the people that took it on the early day, you want to not advise or not tell anybody else what was on it. One, because that's cheating, but two, because you're going to give them an advantage, which ultimately will harm you. Because if the class average is higher, which it would be if you tell one person, you're almost certainly going to find out that that person told other people, and next thing you know, the class average is 10 points higher than you, and you were the sucker that made it happen. So just be careful with that. But generally there'd be a randomness to it. So like I have multiple, if I did it online with the multiple choice, there would be several different versions where, I have one type of question, but there's three versions of it. And each time someone opens a test, it picks one of those. That's what it does for each problem. Uh, If it's a paper one, then I usually have like a test A, test B, test C, test D, and those are sometimes just different orders, but sometimes they're different orders and different numbers. So that the tempted student might look over and see a problem with the same diagram as the problem they're working on and copy your answer. Well, guess what? That might have the entirely different number, so your answer's wrong. So that's what I do to try to be mindful of cheating. I pride myself on being pretty good at catching cheating, so that's why I always have special little ideas about that. When you have a minute, would you mind checking your? Yes. Yeah, I will check that, Noah. I have not been very good on my emails. I have been much better on checking my text messages since I've been sick. But yeah, Noah, I will definitely do that. Uh, Hussam, your hand is up. Oh, okay, gotcha. It just went down. Did you have a question, Hussam?
No, no, I was gonna ask about the paper thing before, but I just asked you.
Gotcha. No problem. So and as far as scratch paper and stuff like that goes, I'll have that for you. Man, I got a newborn head. My hair so it's like time to get it cut, and now it looks like a ratty old baby. So a neglected baby. All right. Anyways, yeah, after the exams are done, you don't have any more time meeting me. That's part of what I do by offering all these different times. That's me fulfilling my hours to you guys every week of the semester. You are allotted basically what we'd call probably 3 + 3, about 6, 7 hours roughly. So either on the exam week when we have one day that's supposed to take 3 hours, I still owe you a few more hours. So I always make sure I'm around for office hours. I usually do some office hours the week before that are a little bigger than normal, and I do some office hours the week of, and I give all those different times so that I'm here, make sure I'm here for a full amount of hours for each student available. So yeah, when you finish your exam, you're done with the course. You don't have to come back for anything. Uh, and Hadi and Hussam, y'all missed y'all were a little late. I didn't see Alyssa might have been, but y'all might have not been here when I mentioned what I'm doing with the homework. So when the video is posted, go back and check the beginning of it. It's a little too much for me to say, but or someone can chat it to you. But either way, that's what's going on. I've told them about the homeworks and everything. So let's get started on chapter 15. Remember, I did advise you on chapter 14. It's just there's a lot of complicated stuff in chapter 11, good stuff, nothing that I would necessarily say is too hard for you guys, but I'm trying to pick out for the practice final, I'm trying to pick out just the ones that are simple conservation of angular momentum problems. And for chapter 10, obviously conservation of energy and torque problems. But when we go to 14 and 15, I'm cutting it down to just this material I'm getting ready to show now. So let's go ahead and get started. I'm going to go ahead and share my screen. And by the way, your attendance is here. If you're finding it not that helpful, if you're finding this would be more useful time for you to work on your your face-to-face test redo, then you're free to go. I'm not taking roll in that sense. I'm not, I never take roll as a penalty or whatever. But by all means, if you think that's a more useful thing of your time and you've got time constraints, you can do that, and you can check this video out when you get when you get a chance. Similarly, if you feel like you should be working on your practice final, that's not made yet, but that would be another reason to not show up to an office hour. So, anyways, just letting you guys know that I understand that you guys are college students. You're supposed to, understand what's best for you. If you have a time constraint that doesn't allow you to stay here this whole time, that's fine. But I do think there's some good, valuable information on it. But you can fast forward through a lot of crap like me talking right now. All right. Okay. So now I'm doing the sharing of the iPad screen. That's the longest I've ever taken to do that. Oh, and I misplaced my glasses. That's always awesome. Okay. Now I got them. Now I'm sharing the screen. I'm sharing the screen. I swear I'm sharing the screen. There it is. Okay. So we now have that. So what I'm starting off with, as I said, was chapter 14, which is called oscillations. And I'm surprised but I did discover the other day a person even older than me that had never seen the word oscillations. So I figured I might should pronounce it a couple times because I heard that person pronounce it oscillate with a C, with a hard sounding C. It's oscillate, and it just means to move back and forth, basically. So motion that goes back and forth or repeats itself in time, that's what we call oscillatory motion. There's a very specific instance of that called simple harmonic motion, and that's what we're going to learn about now. We're going to learn about simple harmonic motion, then we're going to learn about damped harmonic motion, then forced harmonic motion, and a lot of neat little stuff. But all of it's really about recognizing a differential equation and then recognizing how to adjust the solutions for that, given the change of certain variables in the problem. So as I said, we're on chapter 11. It always opens with a nice chapter opening question, so you want to check out that. What I'm going to start off with, though, is Hooke's law. You all recall that Hooke's law says, Hooke's law says that the force is equal to negative kx. And remember what that means is if you stretch an object. Now, we normally do springs, but as I told you before, we do springs because springs allow us to look at stretches and compressions with very small forces. Where if I took even, even a wood dowel and I tried to put enough force on it to compress it or put enough force on it to stretch it, you've actually created a dangerous force situation. Like the force is so big that the thing could become a projectile and actually harm someone. So spring is a much better use. Additionally, what Hooke's law tells us is that when you stretch or compress a string by an amount x or negative x, in other words, x is positive 2 centimeters, we would normally treat that as if it's a stretch of 2 centimeters. Whereas x is negative 2 centimeters, that would be in turn considered to be a compression of 2 centimeters. But the cool point about this is that the force right here is given by negative kx. So if you stretch the spring in the positive 2 centimeter direction, so that in other words you actually stretch it from the equilibrium position to 2 centimeters farther away, then the force is going to be positive 2 centimeters times the spring constant times a negative, which means it's pointing back. So if you pull the spring to the right, just to stretch it, then the spring pushes back to the left. That's what the negative tells you. Similarly, if you compress the spring by pushing it to x equals negative 3 centimeters, then the negative 3 centimeters times the positive k times the negative gives you a positive. And in that case, you're pushing to the left, but the force is pushing to the right. So that's what that negative is in there for. The k is called a spring constant, and we know already that the energy associated with a spring, which we could call a potential energy or a work, is equal to 1/2 k x squared. So the first thing I got to mention to you guys about this, and this is somewhat related to what I heard some of my students in calculus are going through, but there's a really good question at probably in all of your brains is like, why are physicists so obsessed with springs? Okay, it's not that the world is full of springs and all important problems involve springs. It's actually that there's this neat anomaly. If you take a Taylor or Maclaurin series expansion, you can see that when you're dealing with a potential energy function, the spring is a very natural result. So let me show you that right quick. So we know, for instance, if certain criteria are met, and honestly, in the physics world, the criteria are almost always met for these things to converge. But if certain criteria are met, then you can represent a function f of x using a Maclaurin series or a Taylor series by expansion of f about a particular x value. The Maclaurin series, or excuse me, the Taylor series is about x equal a, whereas the Maclaurin series is about x equals 0. And what you do is you say 1 over 0 factorial, because this is the first term, which we start counting with 0, times the 0th derivative, which means the function itself, that function will be evaluated at 0 and then times x to the 0 power. Then the next term would be 1 over 1 factorial f prime. So that means the first derivative evaluated at 0 times x to the 1 plus 1 over 2 factorial. Notice how we're increasing each time. The second derivative evaluated at 0 times x squared plus 1 over 3 factorial f triple prime 0 x cubed plus dot dot dot. So that's what the Maclaurin series expansion is for a given function f of x. So what I want to tell you is, let's imagine that f of x is an energy. If that f of x is like a potential energy,
So your voice went down.
oh yeah, I'm not talking yet. Sorry,
Oh,
but
okay,
thank
you're
you.
good.
Yeah. So imagine f of x is a potential energy function. If that's the case, then what I want you to think about is a lot of the world of physics, especially at the microscopic level, is us examining the conditions near equilibrium. Okay. So if you thought about, or if you read about equilibrium conditions in the previous chapters, what you know is equilibrium states tend to look like this. So right in here is equilibrium. I always want to put two L's in there, so I apologize if I'm misspelling it. It might be two L's, might be one. I don't care that much, but I do look it up normally for if I were to type it and put it in something. But anyways, right there is roughly the equilibrium. Now, the reason I say that is I want you to understand that, remember our potential energy. For instance, we had U equals mgy, but it was okay, for instance, for us to say the y equals 0 outside on the sidewalk of our campus. But it was also okay to say y equals 0 at the first floor. But it was also okay to say y equals 0 at the second floor. So literally the height of the second floor. And the reason why that was the case is it turns out that only the difference in potential energies is relevant in the vast majority of cases. Because of that, you can add any arbitrary constant to a potential energy function, and it's still the same potential energy function. It's still going to give you the same important information. So when you think about that, you can already think that, well, one term can just be arbitrary. So if you look at f of x, then one of these terms could be completely arbitrary. If you look about, well, I'll say this implies a potential energy function can have an arbitrary constant added. So we reached that conclusion. Now, can anybody tell me if this function right here is f of x? Okay. Can anybody tell me what the derivative would be right there? The dot I just drew.
Zero if it's like horizontal, if that's what you're going for, like
Yeah. Yeah, exactly. So equilibrium implies df over dx, which is what we called f prime of x, is on the order of 0 there, right? It's very, very close to 0. Now, in addition to that, we have as I said, an arbitrary constant. So let's look right now at our f of x. This could be an arbitrary constant. And near equilibrium, whoa, the extra e was not supposed to be there. This term's approximately equal to 0. So basically what we have now is just this term right here, which is 1/2, because 2 factorial is just 2 times 1, times a constant, specifically the second derivative of the function evaluated at 0. That's just a constant. Of course, any function evaluated at x is a constant, whether it's a derivative of a function or not. It could be a constant at 0, but it's generally a constant long as the thing's differentiable. And then it's times x squared plus ... and these terms are successively smaller. It said somebody came in, but it's not allowing me to see it. Maybe somebody just left. I don't know. All right. So these terms get smaller. I just leave it like that. These terms get smaller. So what we've basically done is we've imagined an arbitrary potential energy function, f of x. We've expanded it in a Maclaurin series. We found that it's basically a constant plus, if we happen to be near an equilibrium position, that second term is 0. And then all we're left is 1/2 a constant times x squared, which happens to be exactly like the potential energy of a spring, 1/2 kx squared. So that's why physicists study. There's the person. Okay. That's why physicists study springs so much. It's not because, we're just obsessed with springs. It's because it turns out when we're studying near equilibrium, the potential is always going to look like a spring. In fact, you might have asked, once you eventually take a quantum mechanics course or run into any real training in quantum mechanics, one of the first and somewhat surprisingly difficult problems to solve in quantum mechanics is one where you have a harmonic oscillator. And you're thinking, well, why the crap do you have a harmonic oscillator? There's no springs that are the size of molecules and atoms, of course. Well, it's because of this. The potentials act just like a spring. And in fact, when they saw that, they got information that was useful, even though they had no model of it to be applied necessarily to an atom or anything like that. They just imagined a harmonic oscillator. And we got the 0-point energy, which, of course, allowed that really horrible bad guy in The Incredibles. He made the 0-point energy weapon, and he could have taken over the whole world. Of course, I know that's a fictional movie, but still, just bearing that back, that the 0-point energy is a famous result from quantum mechanics, and you can get it just from that simple thing. And it turns out to be very important. In fact, later, Dirac solves the harmonic oscillator problem in a really weird way. We eventually call it space quantization, which is not necessarily correct, but that's the invention of quantum field theory at that point. And that again came from the quantum harmonic oscillator. So, anyways, that's enough on that. That's why we study the harmonic oscillator. I'm going to go ahead and line this off to separate it from the rest. I hope that makes some sense to you folks about why we do it. Now I'm going to go on with the rest of this, and I want to let you see how something works. One thing we know is that from rotational motion, we know omega. Whoa, Nelly. We know from rotational motion that omega, called the angular speed or angular frequency, is equal to, I'm going to go ahead and write that out. Darn it. Is equal to 2 pi times f. We also know that f is equal to 1 over t. So you can also say that omega is equal to 2 pi over t, where t is the period. That's the period of oscillation. And f is the frequency. I should say that f generally has units of hertz or cycles per second in some old terminology, or revolutions per minute, ... All those are fair game. T normally has units of seconds, and omega in general has units of radians per second. And if you stick with radians per second, all the equations you have with it will always work. But if it's not radians per second, it may or may not work. So now that I have reminded you all of those facts, I'm going to use those from here on out to make sense of certain problems. So let's start off with example. Whoa, Nelly. Let's start off with example 14.1. So this basically says a family of 4 with a total mass of 200 kilograms, which I'm going to assume is 3 sig figs, step into their 1,200 kilogram car, which I'm going to assume is 4 sig figs. Okay. So when a family of 4, total mass M equal 200 kilograms, step into their 1,200 kilogram car, the car's springs compress X equals 3 centimeters. I'm going to make that 3 sig figs, like that. A, what is the spring constant? So they want to know K equals question mark. That's part A. What is the spring constant of the car's springs, assuming they act as a single spring? And then for part B, they would like to know how far will the car lower if loaded with 300 kilograms rather than 200 kilograms? Okay, so those are our 2 questions. Again, this one's actually from the book, so you can actually read it, but I'll read it one more time. When a family of 4 with a total mass of 200 kilograms step into their M equal 1,200, that's capital M, equal 1,200 kilogram car, the car's spring compresses 3 centimeters. What is A? What is the spring constant of the car's springs, assuming they act as a single spring? And B, how far will the car lower if loaded with 300 kilograms rather than 200 kilograms? So what I'm going to do is say solution. And I'm going to use the equations that I think are going to be necessary. So F is equal to negative KX, which I usually just drop the negative when I'm solving problems like this, and that's okay. Remember, the negative is about the direction, not about the magnitude. So we have that. And that should be all we really need to use. So for instance, for part A, I'm going to say the actual weight put in the springs or in the car is the 200 kilograms. The car was already sitting there on springs and it already established an equilibrium position. Then you're adding 200 more kilograms, which is not a force, so we got to make it a force. And the way we make that a force, actually, that's another equation I could put on there. The way we make that a force is weight is equal to mg. So now I can say 200.0 kilograms times 9.80 meters per second every second is equal to, here's where I'm dropping the negative, K times 0.0300 meters. Notice how I did put everything in the conventional SI units. So now I can figure out that K is in fact 200 times 9.8, which gives me 1960 newtons divided by 0.0300 meters. And that gives me 6.5333 times 10 to the fourth newtons per meter. That's the spring constant. Okay, so that's part A. Anybody have any questions with that? Notice how I do box it. Notice how I also put the A up by the corner. That's important if you're doing a handwritten test, a handwritten solution. I want the final answer boxed off. Notice how I did put the units in too. Notice also that you don't always have to know exactly what equations you're using as soon as you write the solution up there. You just leave a line and you can put them. And it's also not that critical as long as somewhere I see the actual equations that you applied in their true sense. In other words, without all the numbers in it and stuff, I need to see the equation written once as it's written in the book or on the equation sheet before you put the numbers in so I know exactly what equation you're using. Now that I have that, we're going to try to use the K to determine part B. So for part B, what we know is now we're going to do 300 kilograms. So again, we're going to say F equals KX. That's going to give me 300.0 kilograms times 9.80 meters per second every second is equal to K, which is 6.5333, carrying my classic 2 extra digits, times 10 to the fourth, times X. And of course, we can now solve for X. And I'm not necessarily going to show what it is. I'll read it out because you can all clearly verify this calculation. So we're going to do 300 times 9.8. That's going to give me 2940. So 2,940 divided by 6.5333 times 10 to the fourth. And that gives me 0.0450 meters, which is 4.5 centimeters. Notice the weight is 1.5 times bigger than it was in the original instance because 1.5 times 200 is 300. And lo and behold, the stretch is 1.5 times bigger because the first stretch was 3. Half of 3 is 1.5. So 3 plus 1.5 is 4.5 centimeters. And that's exactly what we got. But that's the nature of a linear equation like F equals KX. If you double the F, then you double the X. If you triple the F, you triple the X. If you cut the X by 1/4, you cut the force by 1/4. Okay. All right. So we've gotten that one. That's just a little bit of an idea of getting used to what K is and that sort of thing. So that should have been really, really easy peasy. Now what I want to talk about is simple harmonic motion. What we know for a fact is that when you have a force that's a restoring force, like the F equals negative KX, then that has the ability to make a simple harmonic motion. Okay, so F equals negative KX is a restorative force specifically because of the negative. So then they have a conceptual problem, a conceptual example 14.2, and they ask you which of the following forces would cause an object to move in simple harmonic motion. They've got F is equal to negative 0.5 x squared. They've got F is equal to negative 2.3 y. They've got F is equal to 8.6 x, and they've got F is equal to negative theta. Okay. Now I can tell you that f equals negative 0.5 x squared has that restorative component with regards to the negative sign, but because of the x being squared, that completely cancels it out, because if you had a negative x, once you square it, it's going to become positive. So the force is really not restorative. So we can eliminate A. F is equal to negative 2.3y. That's just like f equals kx, or just using the y variable, and it even has the negative in it, f equals negative kx. So that one is definitely a simple harmonic motion force. The f equals 8.6x, that does not have a negative. So that's actually kind of force that if you stretch it by an amount x, the force gets bigger, and it never tries to bring it closer back in. It doesn't have the restorative effect. But finally, you get to f equals negative 4 times theta. That again is restorative, and the fact that it's theta doesn't really matter. You can still have a positive or negative angle. So it's really just B and D that are simple harmonic motion functions. Again, that's something that's very detailed from the book, but I'm now going to show you exactly what the differential equation is for simple harmonic motion, and I want you to sort of commit this to memory, even though it is on our equation sheet. So if you were to imagine Newton's second law says the summation of all the forces is equal to mass times acceleration, but in reality, that's d2x over d2 squared. Actually, in vector notation, I've been using not x for the position, but in 3 dimensions, I generally use the variable r as a vector. So that's really what it should be. And of course, that reduces to the summation forces in the x direction equals mass times d2x over dt squared. The summation of the forces in the y direction equals mass times d2y over d t squared, so on and so forth. The main thing to notice here is, yes, we did learn that m dx d2x dt squared is not necessarily the way Newton's law is written. It's supposed to be dp dt, but this is a case where you're not losing any mass, so it's certainly fine. Now, what this could represent, for instance, is a spring mounted on a wall above a floor that is nearly frictionless and is in equilibrium. So we could put a little mass over here, and we could say that this position right here is our y-axis, so this is equilibrium as well. And then what we could do is say that this is our positive x-axis, and that's our negative x-axis. Okay, and again, I'm assuming there's no friction. If we take the summation of the forces in the x direction equals mass times d2x over dt squared, then what we'd have is literally only the force negative kx is equal to m d2x over dt squared, which is not the way we generally like to write this. We generally put the orders of derivatives in decreasing order. So the highest order derivative would come first, then the second highest, and the third highest. And then we also, a lot of times, will divide through so that there's no leading coefficient. So what I'm going to do is write this a couple different ways until I get it right. M d2x over dt squared plus kx is equal to 0. And now I can say d2x over dt squared plus k over mx is equal to 0. And that is the simple harmonic oscillator differential equation. So this is the simple harmonic oscillator diff equation. Okay, notice it's a second order derivative. It's a ordinary derivative. It's not a partial derivative. It's a second order derivative followed by a constant times a 0th order derivative, in other words, just the x, and that's equal to 0. Now, the way you would do this in a differential equations class is they would say, well, first off, let me explain why they would do this. If you were asked to do this in a differential equations class, the way they would teach you this in the differential equations class is they would say, hey, look at this. We know that if we take the derivative of one function and it pops out the same function again, then that could be a type of function that could actually solve the equation, because if the d2x over dt squared was just a constant times the original x, plus now you have the other part of the equation that says k over m times x plus some constant times x, you can see that there's just one unknown, and that's x, and you can solve it really easily. So their idea is, hey, maybe we should consider e to the x, because the derivative of e to the ax is just a e to the ax, and the second derivative is just a squared e to the ax, and the third derivative is a cubed e to the ax. So that's the idea. So they're going to say, for this one, let's try a solution. So let x equal a times e to the row t. That would be what they would try. And then they say, well, dx over dt is equal to a row e to the row t, and d2x over dt squared is equal to a row squared, a row squared e to the row t. And then you could plug all that in, you'd see a row squared e to the row t plus k over m times a e to the row t is equal to 0. This differential equation has to be true at all time t. Okay, so that's a very special thing. What I can do is factor out a common term, and I'm going to see that I have a times e to the row t common to both terms. So that's going to give me row squared plus k over m is equal to 0. And like I said, it has to be true at all times. Therefore, row squared plus k over m has to equal 0. If you made it equal 0 by putting something in that t, well, you'd find that it can't be, because there's no way to make an exponential into 0. So all you have left is this, and then that tells you that rho is equal to plus or minus I times the square root of k over m. And that would be fine. Your book does it an entirely different way, and he makes use of the fact that we know, which, by the way, this way will ultimately work out to. It just takes a ton of algebra to get there, but you can get there. But it does the same thing, except it realizes that, hey, the end of this, we're going to have a sine function or a cosine function, so you might as well do it. And part of the reason we think that is this Euler identity, which says e to the I theta is equal to cosine theta plus I sine theta. Whoops. Like that. Okay. So you can see that E, when it's raised to an I power, some power with an I in it, it becomes a sinusoidal function. So there's a real part, an imaginary part. The real part is cosine theta. The imaginary part is sine theta. You can actually prove this by just doing the Taylor series expansion of e to the I theta, the Taylor series expansion of cosine, the Taylor series expansion of sine, and you'll just pick out the terms and see that it's true. So let's jump away from that for just a second, because I've covered more or less what you would do in your differential equation class. But in our physics class, what we do is we say, let, well, I hate, let x equal a cosine omega t plus phi. So what your author's doing is he realizes that being a second order differential equation, you should be able to make sense of this. Let me explain it to you. Second order differential equation means it's a derivative that's been taken twice. What mathematical function undoes a derivative? Anybody?
Integration.
Exactly. In fact, that's why they called it an antiderivative when you first were introduced to it. But yeah, it's integration. So when you integrate just an arbitrary function without any limits of integration, what do you have to put on the end?
Dx.
Yeah, you have to put some kind of constant on the end, right? A constant of integration.
Mhm.
I think I heard you right. So you can imagine that if you undo one derivative, you're going to have one constant. If you undo two derivatives, you're going to have two integrals and therefore get two constants. And that's the nature of a differential equation. It's a second order differential equation. So I'm going to have two initial conditions to make sure that I can get the function in its entirety. That means there's at least two unknowns. In this case, we've got an unknown in A, we've got an unknown in omega, and we've got an unknown in phi. But what you're going to see is one of those is dictated by that characteristic equation, which in this case was the p squared, or the rho squared plus k over m equals 0. One of those is going to be filled up by that, and then your two initial conditions will allow you to determine a and phi. Okay, so we let that be the case, and then we say, all right, well, dx over dt, the derivative of cosine is negative sine, so I'm going to get negative a omega sine omega t plus phi. Remember, you got to use your chain rule. So when I take the derivative of cosine with respect to t, I take the derivative of u with respect to u, and then I take the derivative of u with respect to t, and that's where I got the omega that popped out in front. Now the second order derivative, t2x over dt squared, is equal to negative omega squared a cosine omega t plus phi, like that. So now I can plug all this into the equation, and what I'm going to get is negative omega squared a. Sorry about that. Negative omega squared a cosine omega t plus phi plus k over m a cosine omega t plus phi. All that is equal to 0. So you can factor out the thing they have in common, which of course is a cosine omega t plus phi, which equals 0 on several instances, but not at all times. So that can't be set equal to 0 to find our solution necessarily. But what we have left is basically just omega squared plus k over m is equal to 0. It has to be true at all time. Therefore, omega is equal to plus or minus the square root of k over m. Now, you don't necessarily know what that plus or minus is. It's actually plus or minus I. Oh, excuse me. No, that one was negative. Sorry about that. So that is not plus or minus I. You can see the advantage of Giancoli and physicists in general doing it this way. We now got omega squared equals the plus or minus square root of k over m, but we've got no I in it, so that makes it a little easier. So now we can say the solution x of t is equal to a cosine square root k over m times t plus phi. So all we have left is to solve for a and phi. Initial conditions. Okay. You could have, for instance, that, oops. You could have, for instance, that x at t equal to 0 is equal to, let's say, let's just call it x0. Okay. And another condition we could have is v of t equals 0, which is dx dt at t equals 0 is equal to v0. So that's another thing we could have as well. So if I were to apply these two conditions, what I'd see is, first off, let's apply it to x of t. So I'm going to say x0 is equal to a cosine of 0 plus phi, like that. And that, of course, tells us that phi is equal to the cosine inverse of x0 over a. So this is one of the constants that we need. Now, if I take the velocity initial condition, what that's going to be is, notice our velocity was calculated in the first derivative, which was this guy. Okay. So now what I'm going to do is I'm going to set V0 equal to negative a omega sine of 0 plus phi. Now, we're going on the assumption that we know phi, so we can, in fact, make a right triangle out of phi. What we know, for instance, is the cosine of phi is equal to x0 over a. So cosine is adjacent over hypotenuse. So that's x0 here, and that's a here. So this must be the square root of a squared minus x0 squared. So we know that the sine, therefore, of phi is specifically opposite over hypotenuse. So this guy we can replace with square root a squared minus x0 squared divided by its opposite over hypotenuse divided by a. So with that, we can go ahead and find out what a is. So actually the a's cancel out, and we can find out, no, those cancel out, but an easier a does not. So I'm going to take this and pull it to the next page. Copy. Nope. Okay. So this is what we were just working with. Let me erase that part. I don't need it. That part, I don't need it. So what I'm going to get is, writing in red again, negative a omega square root a squared minus x0 squared, all that divided by a. You can see now what I was talking about, those a's cancel out, and I get v0 equals negative omega square root a squared minus x0 squared. So now I can square both sides. That would give me v0 squared is equal to omega squared times a squared minus x0 squared. And we can then call that v0 over omega squared is equal to a squared minus x0 squared. So a squared is equal to v0 squared over omega squared plus x0 squared, or a squared is equal to v0 squared plus omega squared x0 squared over omega squared. So A is just equal to the plus or minus square root of V0 squared plus omega 0 squared x0 squared over omega. And now we have the other equation. So that's really what you could use to solve your differential equation. So really, to be honest with you, using that, which I do not put on your equation sheet, by the way. So using this expression for A and then using this expression for phi always works. Okay. All you have to do is if you see an equation that has a second order derivative plus a constant times the x itself equal to 0, your solution is x equals a cosine omega t and plus phi, and the a and phi are given by those equations. Does that make sense to everyone? All right, so let me circle off this equation too, because that's what our solution is. So the most important things are all have boxes around them now. You can see the simple harmonic oscillator equation. You can see its solution. You can see how to find phi in the solution. And now you can also see how to find A in the solution. Okay, there are cases where it's a lot simpler, by the way. It's just I did the most general case possible, so it looks a little more confusing than it necessarily needs to be. Let's go ahead and look at an example because I want you to understand how much easier it is than it appears. All your job is to do is to recognize the differential equation, d2x over dt squared plus constant times x equals 0. Know that it has a solution, x equals a cosine omega t plus phi. Know that you can easily solve for a and easily solve for phi, as I just did. And if you want to commit to memory these things, and by the way, it doesn't necessarily matter what the plus or minus is. Well, it does. If you actually pay close attention to what V0 is, that would give you some indicator. So for instance, you would expect if the initial position is smaller than the amplitude of oscillation, in other words, smaller than A, then you'd expect the velocity when it's at a smaller position than A, obviously, the velocity should be pointing in that same direction so that it slows down, slows down, slows down to get to A. So that can help you understand better whether the A is upside down or the A is positive or negative. Because remember the graph with A out in front, the A is the amplitude of the cosine wave. Right? So if it's a negative, instead of starting on an upswing like cosine does, it's going to start on a downswing. So you got to pay attention to that. But these results basically work. So let's look at example 14.3. And it'll get a lot less I don't know, pain in the butt wise after these examples, because you just got to do a couple of simple ones and explain the differential equation stuff. Now it says in this one, the car is in spring again. Determine the period and frequency of the car in example 14.1. The period and frequency of the car in example 14.1 if the car hits a bump. And we're assuming the shock absorbers are really poor, so that it really go sort of. I don't know if you ever saw the movie Uncle Buck, but when he hit a bump, it like continued to hop up and down for several minutes. Okay, that's what shock absorbers do. They're supposed to dampen the oscillation. You might also remember an episode of The Simpsons where someone pushed his stomach and it jiggled. And he said, "Woohoo, look at it go." And it lasted for a long period of time. So, anyways, you can think of that. All right. So, with this in mind, what we know is solution. We need period. We need frequency. We know frequency is equal to 1 over period, and we know omega is equal to 2 pi times the frequency. But we also know omega is equal to square root of k over m. We already worked out what k was, so we can now say part A, omega is equal to the square root of 6.5333 times 10 to the fourth newtons per meter divided by, we're assuming the initial mass, which was the 200 kilograms. Oh, actually, excuse me. This has to be the whole darn thing. So that's 200 plus 1200 is 1400 kilograms. Okay. Now we can do this computation. I'm going to say 6.5333 times 10 to the fourth divided by 1400. That gives me the square root of 46.666. And of course, those units turn out to be reciprocal seconds squared. Well, seconds to the negative 2 power there. So that's the actual units. And then when I take the square root of that, I get 6.83 or 8313. And that's radians per second. So that's omega. And what we're asked for first is the period. So what we know is omega is equal to 2 pi f, and we know f is equal to 1 over t. So we can say this is 2 pi over t, and that means t is equal to 2 pi over omega, which would be 2 pi divided by 6.83. And remember, the radian is a unit that you can just slop off anytime you want to. So I'm going to take 2 times 3.14159, and I'm going to divide it by the 6.83. And that gives me 0.91977 seconds. And that's 2 extra digits, as always, with me. So we've got that. And your book was calling that 0.92, which I use 3 sig figs. They use 2, so that's perfectly reasonable. And now they want to know the frequency. Well, we know for part B, frequency is equal to 1 over the period. So we can say the frequency is, I'm just going to raise this to the negative 1 power. And that gives me 1.0872 hertz. And that's also read as cycles per second, but that's the frequency of oscillation. Okay. So that's some really simple stuff. But now it's going to start to get a little more weird, and this is the part that I need you to understand. So the very next example, it says a spider of mass 0.30 g waits in the web of negligible mass, a slight movement causes the web to vibrate with a frequency of about 15 hertz. Estimate the value of the spring stiffness constant K for the web. B, at what frequency would you expect the web to vibrate if an insect has a mass of 0.10 grams is trapped in addition to the spider? So what we're doing is something that's very, very abstract compared to the original problem of a mass on a spring. But what they're saying is, hey, we've seen spider webs and they do oscillate, right? And he's even given you an idea of how a spider might know, uh, even in the long distance of a web, whether something's in his web or not, basically by noticing the change in frequency. So let's work this problem. It's kind of neat. I like it that way. So this is example 14.4. It's what they call an estimate one, so they're not really expecting more than 1 sig fig, but they're saying the mass of the spider is equal to 0.30 grams. I think the spider they got in this picture is way bigger than 0.03 or 0.30 grams. That sucker looks scary. Ugh, I hate spiders. I actually touch them and stuff. Just what I do to avoid being afraid of things and stuff like that is I just face them. But it's not necessarily smart. I just happen to know which ones are poisonous, so I don't worry about it. We found the frequency F is supposed to be 15 hertz. And what we want to know is what is the spring constant. So K equals question mark. That's part A. And then part B, what was the frequency be if you expected a mass of a insect is trapped in the web? So for part B, we're going to say F with M insect equals 0.10 grams. So we want to know that frequency. I'm going to do solution. Now what I know here is omega is equal to the square root of K over M, but I also know it's equal to 2 pi over T. Oh, I don't want 2 pi because they did ask for K. But I don't want it in terms of T, I want it in terms of F, so I was thinking of the other problem. So I'm going to say omega is 2 pi F. Therefore, we can say that the square root K over M is equal to 2 pi F. That means K over M is equal to 4 pi squared F squared. So K, and you don't have to solve it this way, I just did it this time. K is going to be 4 pi squared F squared times M. And in this case, it's going to be 4 times 3.14159 squared times 15 hertz squared times 0.30 grams. So K is going to be equal to 4 times 3.14159 squared times 15 squared times 0.3. Oops, that should be 0.003. So let me do this. I forgot to change this. Times 10 to the negative third. Because it's got to be in kilograms. So I almost screwed that up. But it looks like I took care of it now. I got everything out. That should come out to be kilograms per meter squared or per second squared, which is a Newton per kilogram. Yeah. Or Newton per meter. So with this, I get 2.6. And I only had 2 sig figs, so I'm going to say 2.66 Newton per meter. Like that. That should be my spring constant K. Anybody have any questions on that? Now for part B. That was part A. For part B, they want to know what will the frequency be with a slightly different mass. In other words, instead of having 0.3 grams, we're now going to have 0.3 grams plus 0.4 grams. So what we're going to say is 2 pi f is equal to the square root of k over m. So we're going to say f is equal to 1 over 2 pi times the square root k over m. We just computed what k is. So we'll put that in there. That's 2.6. Now I'm going to carry a couple extra sig figs here. That's 2.6. I carried one extra sig fig before and just called it 6. That would probably be enough, but I'm going to add another and just call it 6.5. And that's newtons per meter divided by 0.40 times 10 to the negative third kilograms. So I'm going to take this 2.665 and I'm going to divide it by 0.4 times 10 to the negative 3. I'm going to take the square root of that. And now I'm going to divide that by 2 pi. So parentheses 2 times 3.14159. Like that. And close parentheses. So now what I get is the answer is F is equal to 25.98 hertz. So you can see by adding this extra 0.10 grams to it, the frequency went from 15 to 25 hertz, or more or less 26 hertz. Well, with that in mind, yeah, checking something. 2.665, I did all that right, right? Three was there, okay. I got the 2.7. 0.4 times 10 to the negative fourth. Anybody find any mistakes I made? Because I'm looking, I actually just looked at the answer, and I think your book might have got a different answer than I did. We could substitute into equation 14.7. Oh, yeah, duh. Instead, we notice the frequency decreases with the square root of the mass. The frequency decreases with the square root of the mass. That's true. So higher mass means lower frequency. Then why did I get a higher frequency? That's okay. Notice that was why I looked at the solution, because I got a 25. I actually expected that to get a lower frequency instead of a higher frequency. So anybody want to check my math here? Six five divided by 0.4 times 10 to the negative 3. Take the square root of that. 0.5. This looks like an entirely different number. Let's see, divided by 2 times 3.14159. Ah, there you go. All right, I got the right answer the second time. I must have done something wrong in the calculation. All the numbers are right. Y'all get it too?
Yeah, calculator gave me the right answer exactly. So
Thank you. I appreciate that. Yeah, I got F is equal to 12.99, which both of those are extra digits, and that's hertz. So yeah, we do see that wasn't quite as big of a change as like I was advertising a second ago, because 15 to 25 is a really big change, even though it went the wrong way. But it's still a noticeable change at 13 hertz versus 15 hertz. Obviously, the spider can sense a little different, so that's kind of neat. But notice how it had nothing to do with the spring. It had nothing to do with the harmonic oscillator equation, but yet we can apply it and get some fairly useful results. There's another one like that in here where we're working a problem where you're on a floor and the floor is vibrating due to a big piece of equipment. That's another type of problem. So let me show you that one real quick. So we're going to say example 14.5. And this one says a large motor in a factory causes the floor to vibrate at a frequency of 10 hertz. So F floor equals 10 hertz. This is another estimate problem. The amplitude of the floor's motion near the motor is about 3 millimeters. So we're going to say A is equal to 3.0 millimeters. Notice how I'm picking out variables to assign these numbers. A large motor in a factory causes the floor to vibrate at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3 millimeters. Estimate the maximum acceleration of the floor near the motor. So A max is the question mark. Now, this might seem really foreign, but remember what we got. We found that X is equal to A cosine omega t plus phi. We found that V is equal to negative omega A sine omega t plus phi. And then we found that A, the acceleration, which is the second derivative with respect to time, that is in fact equal to negative omega squared A cosine omega t plus phi. So if you look at this, you see that the velocity oscillates like this, and you see also that the acceleration oscillates like that too. But what you notice is the max, A max, is equal to negative omega squared A. But if you're talking about max, you might as well just say the positive quantity because really all they mean is really the maximum amplitude. So all we have to do to calculate the maximum acceleration is take the frequency in radians per second, square it, multiply it by the magnitude, or excuse me, by the amplitude, and that would give us the actual acceleration. Now, let me tell you, when you go to design a house, let's say in California, it turns out that you have to build for seismic loads, which is earthquakes, and earthquakes are mainly determined in terms of gravitational acceleration. So they literally use as a design spec the actual acceleration laterally that the house should get. So this kind of thing is exactly what structural engineers have to account for when they go to take, for instance, spec the floor joist in a factory that had such a motor in it. Okay, so this is a neat problem. Again, just quick back of the envelope calculations. What we know is omega squared, which is 2 pi f. So I'm going to say 2 times pi times 10 hertz squared times 3.0 times 10 to the negative 3 meters. And then all I have to do is multiply 2 times 3.14159 times 10. And now I'm going to square all that. And now I'm going to multiply that by 3 times 10 to the negative 3. And that gives me 11.84 meters per second every second. And notice that is bigger than gravitational acceleration. So that is something that you sort of have to account for. So for instance, we typically use for a floor in a bedroom like 35 pounds per square foot. In this case, you might want to design it for, instead of 35 pounds per square foot, you might in fact want to do it or twice as big as that, because the gravitational acceleration now is not only 9.8, which is pulling down on it, but it's also going to accelerate at 9.8. So you want to multiply this by 19.6, the quote unquote mass that gives you 35 pounds. You would want to multiply that by 19.6 instead of 9.8. So that would give you some idea of one of the ways you might calculate what to deal with that, what to do with those joists. Any questions on that one? All right, the rest is a lot simpler. You can see that there's various ways where you can find out what's the max velocity. So I want y'all to realize that this right here is V max, just like this right here is A max. And of course, this right here is amplitude. So don't forget your trig functions, that when you graph them, the thing that's multiplied by the trig function is the thing that dictates how high up it goes and how low it goes. That's called the amplitude. When you take the first derivative of x, that becomes the velocity. So the amplitude of the velocity turns out to be the maximum velocity, and the second derivative of x gives the acceleration. So the amplitude of the acceleration gives us the maximum acceleration. Any questions on that? All right, so you should be able to look through the rest of these examples that are like this and make some sense. It's just over and over applying these equations. What I need you to see is now what happens when we add I would go over the energy part, and that's really a wonderful part. It's pretty straightforward, but I'm really trying to focus on what we need. But what I want you to do is definitely read that section, energy in the simple harmonic oscillator, because what you're going to see is in the simple harmonic oscillator. Let me just give you a little taste of what that is. With the simple harmonic oscillator, okay, are they also call it SHM, which is simple harmonic motion. With that, we have E total is equal to kinetic energy plus potential energy, which equals 1/2 mv squared plus 1/2 k x squared. So if you know, for instance, the amplitude, then you know when the object is fully at its maximum amplitude, then you know all the energy is in potential energy, not kinetic energy. So you could say 1/2 Ka squared is equal to 1/2 mv squared plus 1/2 k x squared. You could then solve that for x, or you could solve that for v, and that would always give you exactly what your x is if you solve for x, or exactly what your v is if you solve for v for a given x or a given v anti respectively. Also, if you consider the max velocity, then you can say 1/2 m omega squared a squared is equal to 1/2 mv squared plus 1/2 kx squared. So you could then solve that equation for x or v as well, and again that would give it to you. In both cases, you had to know the total amount of energy, which if you knew the amplitude, you know the total amount of energy has to be 1/2 ka squared. Whereas if you knew the v max, you know the total energy has to be 1/2 m omega squared a squared, because when the velocity is a maximum in a simple harmonic motion, the actual potential energy is a zero. Okay, because like on a swing, if you're thinking about a pendulum, as the swing comes through the bottom, the potential energy is reached its minimum, and therefore you could assign that the zero quantity. Therefore, the kinetic energy has reached its maximum, which means its velocity is a maximum. And then it slows down, slows down, slows down, comes to a stop. At that point, its potential energy has reached a maximum, and its kinetic energy is zero. That's why you get 1/2 K A squared. All right. So that's what the advantages of using energy are, is you can solve for V of X, or you could solve for X of V, meaning if someone said, what's the position, how far is it from equilibrium when the velocity is positive, blah, 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 you can use that X of V to find that. If they ask you for what's the velocity when the position is just 1 centimeter to the left of equilibrium, you could use V of X in that case. Okay. So in other words, solving these equations is what we're talking about. All right, that's enough for energy. I didn't want to really bog down too much on that, but it's worthwhile reading, but I'm going to try to pick very few such equations. Will tell you that in 14.4, he also shows you that it's simple harmonic motion can also be related to uniform circular motion. So for instance, if you wanted to track the path of a let's say a rock in the tread of your bicycle tires, you could trace that and turn out that would obey the simple harmonic oscillator equation. I'm skipping through that as well. It also applies to the simple pendulum. And in the simple pendulum, I got to show you exactly what that is. So with the simple pendulum, you get basically a mass hanging like this at an angle theta, and it's hanging from a massless pendulum. That length is L, and that's to the center of mass of the little ball. And the force acting on it is, of course, since this has a mass M, this would be mg. This would be mg cosine theta, and this would be mg sine theta. And it's a restorative force, so we can take Newton's second law, the summation of forces is equal to mass times acceleration. In this case, we're going to say negative mg sine theta is equal to m times d2x over, or excuse me, in this case, it would be d2x over dt squared. I'll leave it like that. That's okay. The main thing is if you expand sine theta is essentially equal to 1 over 1 factorial times theta minus 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the fifth minus dot dot dot. So you see, for small theta, sine theta is approximately equal to theta. So now we can change the equation to, well, I'll show you, this is the mathematical symbol we often use. Therefore, negative mg theta is equal to m d2, I should call that L theta, sorry about that, d2 L theta over dt squared. Then with this equation, what we get is dividing through by m, you can see that that cancels out, and we get d2 theta over dt squared. L's not going to change, of course, times L is equal to negative g theta. And again, I can make that d2L, or excuse me, d2 theta over dt squared. Actually, I don't want equals. I want to say plus g over L times theta is equal to 0. So does this look like the simple harmonic oscillator? Look at your differential equation right there. Is this the same form as this? It's the second order derivative. Then there's a plus, then there's a constant, and then there's the value that's having the derivative taken of it, the theta in this case instead of the x. So yeah, this is simple harmonic motion again. Okay, so guess what? We've got theta is equal to A cosine omega t plus phi again. Now, you might want to call, instead of that, you might want to say theta of t is equal to theta max. That would be acceptable. Times cosine omega t plus phi. But does anybody know what omega would be in this case? Hopefully y'all figured it out from the way we got the omega last time. Okay, so that's the same thing, and it can even use the same stuff that I did for A, which is now theta, and for phi, you can even use those same equations. So we've now got the right stuff. Is again assuming theta is small. Now I'll tell you, I think what we found out was even at like 25 degrees, it was only off by like 2%. So yeah, theta being small is not that critical of a concern when you're doing the harmonic oscillator, at least in terms of period. The period turns out to only differ by about 2% if you get up to 25 degrees instead of 5 or 4 degrees or something like that. All right, so that's another case of a simple harmonic oscillator. Your book also does a torsion pendulum, I think, and it does a physical pendulum. But in the physical pendulum, we end up getting d2 theta over dt squared plus mgh over I times theta is equal to 0. So this is pendulum. Whoa, that's not the color I want to write in. And this is the physical pendulum. And the physical pendulum is basically just any physical body that has a mass as opposed to just a point mass on the end of a string. Okay. And I is the moment of inertia, and mgh, where h is the different distance between the center of mass and the pivot point. Moment of inertia. And the big thing is, can you tell what the omega is here? So theta is going to be A cosine omega t plus phi. Anybody want to guess what omega is? So what you're supposed to be seeing with all this is just the fact that the simple harmonic motion repeats itself all the time. That was the case of the pendulum and the physical pendulum, and it does a torsion pendulum as well. I'm skipping that completely. Now I want to show you what damped harmonic motion is. So air resistance is what we're talking about here. Air resistance and other dissipative forces. I'm trying to say you could actually, make a pendulum that's underwater, for instance, and that's not air resistance, that's water resistance. So that's what I mean by other dissipative forces. I'm not talking about friction or anything like that in there. So I just want to point that out. But what they have is the force is either proportional to V, or the force is proportional to V squared, we study force proportional to V. Okay, so those are two possibilities. It's a little more complicated to deal with the force proportional to V squared, but now what we have is the summation of the forces is equal to mass times d2x over dt squared, and this is damped harmonic oscillator. Okay, so with this equation, we end up getting negative kx minus b. B is just the constant we're putting in front of it. So negative b v, but v, by the way, is dx dt, and that's all equal to m d2x over dt squared. I'm going to play around with it a little bit and say d2x over dt squared plus b dx over dt plus k x is equal to 0, and then the m is still there. But now I'm going to divide through by m to get it in the more standard form, d2x over dt squared plus b over m dx over dt plus k over m x is equal to 0. So that's damped harmonic oscillator. Okay, that's the equation. I will tell you in this case, x is equal to a times e to the negative gamma t times cosine omega prime of t. And in this case, he drops the phase constant, the phi that used to be on there, where omega prime is equal to the square root of k over m minus b squared over 4m squared, and gamma is equal to b over 2m. You might notice that all these formulas look like parts of the quadratic formula, and that would be exactly the point. Okay, when you plug in a times e to the row t, you end up getting part of it that's actually a imaginary number and part of it that's not an imaginary number. So you end up having three terms that you got to solve with a quadratic equation, and that's what ultimately pans out. The big part about this is there's some complication to it. So for instance, your book says one type motion looks like this, another type motion looks like this, and then another type motion looks like this. Okay, this last case is what we call underdamped. And the middle case, which is what's called curve C here, that's called critical damping. Oops. Now I should say underdamped is a result from b squared being less than 4mk. Critical damp is b squared equals 4mk. So you can imagine now from your knowledge of the quadratic formula that that's probably the case where the square root is 0. Whatever's under the square root turns out to be 0. And that's exactly what happens. In a differential equations class, you would learn that basically you're supposed to have two different functions, like a e to the positive x and a e to the minus x, to be a complete solution. And when you do that, when the b squared equals 4mk, you only have one of them, so you have to multiply it by a polynomial. That polynomial is 1 plus some number times x. And that's what the critical damping curve is. It in fact doesn't even have a cosine. And then this last one is called overdamped. And the condition for overdamped is b squared greater than 4mk. Okay, so those are just things you need to memorize or whatever. I wouldn't even worry about the forced harmonic oscillator, but I will show you exactly what that equation looks like. In that case, you basically just have the same thing. You have m d2x. Well, actually, I'll write it the other way. We have d2x over dt squared plus b over m dx dt plus k over m x is equal to, in this case, some f of t. But it might be a f of x as well. That's the forced harmonic oscillator. I'm not going to make you do anything with that. And we only got a little bit of time left because I plan on trying to let you guys out by 11:50. Again, y'all can stick around as long as you want, but 11:50 is what I'm shooting for. There's a lot of good reading in there. Your job is just to be able to recognize these equations and then quickly know what omega prime is, quickly know what gamma is, that kind of stuff. Now I'm going to go on to chapter 15 and show you the most important part of that. So anybody have any questions on what we have so far? You'll see the problems are a lot easier. I mean, basically, they're more like the examples we've been working. So the rest of this is just you plugging in those numbers, and you'll see it when you get your practice test. I'm about finished with it, by the way. We should have it up in the next couple hours, but I suspect nobody's finished their face-to-face retest yet, yet. All right, so chapter 15 is called wave motion. And what that is simple harmonic motion in space and time. So if you imagine, for instance, throwing a stone out into the water, what happens is the stone hits the surface of the water and then presses the water down, because the surface tension of the water doesn't immediately allow the surface to rip open and the rock to fall through. Initially, there's a little barrier of air between the bottom of the rock and the top of the water, and the water surface tension is holding the water all together, and then it finally breaks and the rock goes through. At that point, what we have is a hole in the water with a hill on each side, but quickly gravity says, wait a second, I've got stuff that's fluid and can readily move and reshape easily, that has a higher elevation in one part than another part. So what I'm going to do is force all this hill to sort of fall into the hole in the water. That's going to basically overcompensate, so it fills it up to flat and then makes it a high, and you've got a trough on each side now. And then the same process repeats, and then it drops back down, and slowly those ripples go outward. So what you're seeing is, if you were at a certain point in space, you would, somewhere else on the pond, you would see the ripple in space go by you. But also, if you were at a different time, you would see a different space. So in fact, what we get is a wave equation, and there's a baby wave equation. And the baby wave equation is just from the definition of velocity, frequency, and period. Velocity is equal to distance traveled on average divided by time taken, right? And if you look at a wave can be plotted in space, and it can be plotted in time. So you could, for instance, have something like this, and then this distance from here to here is not a distance, but a time, and that's called t, the period. Okay? And this is called the amplitude. And this is called the negative of the amplitude. Now, you can also have it in space too. So what we see is this d is equal to d as a function of x and t, not just y. But now the distance from one peak to the next is actually a distance, and in that case, it's called lambda, the wavelength. Okay? And you can look and see that the distance that a wave travels in one period is one wavelength. So you'd say one wavelength over one period. But then you realize that the frequency is 1 over the period. So I can also write this as lambda times f, and that's the baby wave equation. V equals lambda times f. Okay? Now, the V is almost always uh, a square root of something related to force over something like inertia, or something like mass, say. So there's always some kind of formula for a certain type of wave. For instance, the velocity of a wave on a string is equal to the square root of the tension divided by the mass per unit length. We did that in lab. And remember, mass per unit length would be basically weigh the whole string and then divide it by its length, and you'd get a certain number of kilograms per meter, and that would be that. So this is one of the velocities, and in fact, that's the one that helps you figure out, what's the frequency of the guitar string that you're plucking, because it sets up a standing wave, and the fundamental standing wave is just half a wavelength. So the distance from wherever you're fretting it to the bead at the back side of the hole, that is 1/2 your wavelength. So you now know your wavelength, and if you know the tension in your actual string, then you can use that to find the frequency, because the tension would actually allow you to calculate the velocity, and then you can find the frequency. But you also figure out why you do, of course, tighten the string to increase the frequency and loosen the string to decrease the frequency. So all that comes to play in there. But those are two very helpful things. Your book will give you a lot of other ones. What I care more about is your ability to recognize the wave equation and to see what happens to waves when a wave runs over one wave, or when a wave bounces off of a rigid surface, or when a wave bounces off a moving surface. All of that you can get from reading the chapter. There are longitudinal waves and transverse waves. Your book explains that. I'm hoping that's something that you're just reviewing, so I'm not really talking too much about it. Your book does a derivation of the wave equation for a wave on a string. It does them for other ones as well, but the main thing is I want you to know what the wave equation looks like. So for wave on a long rod, you got V is equal to the square root of E over rho, where E, I think, is Young's modulus. No, it's the elastic modulus. That's something you'd learn more about in engineering strength of materials. And this is the density. So you can see it's, again, some kind of force thing divided by an inertia type thing, and that's on a long rod. So you can imagine holding a metal baseball bat down and hitting the end with a hammer. That's going to cause the atoms that you hit to get a little closer to each other. And then that's going to cause the ones right next to it to get a little closer together. And the ones behind it are going to separate. And then the next one's going to get closer together. And then the previous ones are going to separate. And that's going to move along. That's what we're talking about here. That's the velocity of that type of wave. And then there's a longitudinal wave in a fluid, and that's the bulk modulus divided by the density. So this is a longitudinal in a fluid. So this is potentially earthquake type wave as well. When we finish with all that, the wave equation, again, what your book does do or does give us, I'm trying to find it now so that I make sure I use the same symbols. Of course, I'm not finding it now. I wonder if he changed it in the 5th edition. Not yet, not yet. He might have. Not seeing that, not seeing that. Hold on a second. Ah, here it is. Okay, so our wave equation is this. I've got a second derivative. Notice it's a partial derivative. I've got a second derivative of, dang it, second derivative of d of x and t. Now this could be x, y, z, and t. I'm just doing a two-dimensional wave, basically. Second derivative with respect to x is equal to 1 over the velocity squared, second derivative of d, again, of x and t, with respect to time squared. That's it. That is the wave equation. That's exactly the equation that Maxwell found when he put his 4 equations together. And in that slot where the v was, he found the number that they had determined to be the speed of light. And because of that, he knew instantly what light was. It was specifically whatever these d things are, that oscillating in space and time. It turns out that was an electric field oscillating in one plane, a magnetic field oscillating in another plane, and then mutually perpendicular to both of those planes was the velocity, and it was given by a right-hand rule. E cross B gives you V, the velocity. So I really need you to know that equation, and then from that equation, you should understand what the actual solutions are. So the solutions are kind of nice. It's specifically d of x and t is equal to a. Now, for some reason, he decides to use sine here instead of cosine, but that's okay. You could have used cosine, but it's the sine of now k times x minus omega times t. This, excuse me, this travels in the positive x direction. And d of x and t equals a sine kx plus omega t. This travels in the negative x direction. Okay, the way you can see that is you can solve for the argument. You can say kx minus omega t equals a constant. Let's call it chi. Okay, so if you solve for x now, you'd get kx is equal to x plus omega t. And by setting the argument of the trig function equal to a constant, we're saying, hey, we're watching one point on the wave. Maybe it's the peak of the wave, and we're just following that in time. When we do that, what we get is x is equal to 1 over k times this big X plus omega over k times t. This part's just a constant, but this part is the velocity. It's called the phase velocity. Okay, so that omega over k tells you how quick the particular phase is moving to the left and right. But the fact that you see that this is greater than 0 and getting larger tells you it's moving to the right. Everybody get that? If you did the same thing with the other one, kx plus omega t equals x, then you'd get basically or you'd get x is equal to 1 over k, like this, times that big X, and then you get minus omega over k times t, and you see that that gets less than 0. Okay. So all I got to teach you now is that k is 2 pi over the wavelength. And we already knew omega was 2 pi over the period. That's the easiest way to make sense of it there. So we need this. Well, actually, I wanted that in a different color. We need this. We need this. And then we need this and this. And now you have everything you need to know in addition to V phase is equal to omega over k, which notice that would be 2 pi over the period divided by 2 pi over the wavelength, which equals 2 pi over the period times the wavelength divided by 2 pi. You can see that the 2 pi's cancel out, and you get lambda over t, which is the baby wave equation again, lambda f. So you see it's the same velocity. That's all you really need from this chapter. Okay. Read it so you can understand some of the concepts, but you just need to be able to recognize in a wave equation whether the wave is moving to the right, whether the wave is moving to the left. Can you identify what k is? Well, if they gave you the wavelength, you can. Can you identify what omega is? Well, if they gave you the frequency or the period, you can. Can you identify what the amplitude is? Well, they probably have to give you that, but that's the main stuff. And I will point out that the amplitude is sort of the crux of whatever the wave is. So for instance, if the A has units of newtons per square meter, that's a pressure wave. If the A has units of volts per meter, that's an electric field wave. If it has units of Tesla, it's a magnetic field wave. That's all that really matters about the amplitude function. The d of x and t is just that. I will tell you that in general, k is supposed to be a vector, or thought of as a vector. The reason why I tell you that is because in general, if you wanted d of x, y, z, and t, you would say a sine, but instead of just k times x, you would say k vector dotted with the position vector and then minus omega t. So k is supposed to point in the direction of that the wave travels. so it's parallel to the velocity. So that's what dictates whether you get k times x, k times y, k times z, or k times x plus k times y, where there's a different k in front of the x and a different k in front of the y, a k sub x times x plus a k sub y times y, and that sort of thing. So that's the more general version of it, but that's completely it. I've covered everything that I think is critical for you. You'll see when you start doing your practice tests what's expected of you. You are free to go. I am here. I'm going to be available by text message. I'm going to stay here till the last person leaves. So if anybody has any questions, you can ask me them, and I'll stay pretty much for as long as you're willing or wanting me to, unless lunch comes up or something. I might take a break. But other than that, you can text me in real time and send me pictures of problems you're having difficulty with, and I'll be glad to help you with it. Colin, I will check your email as soon as I get off of here. But you guys are free to go. Make sure anybody that didn't do this already, make sure you chat me your first and last name. Other than that, you guys are free to go.
Could you go back to the last page for
Yes.
the wave equation?
Yes.
All right, thank you.
What's helped me remember that is the fact that the velocity is in the bottom on the same side with the time, because if you multiply velocity by time, you get x. So you'll notice that's on the opposite side is the dx. So that's been super helpful for me to remember it.
You for help later.
What's that, Michael?
See you Monday.
Okay, see you Monday, buddy. Dan, did you have any other questions?
No, that was it. I just didn't get to write down the that wave equation.
That's cool. Actually, just I wasn't sure that was your voice that I heard ask for it, and
Yeah.
while you were the only one here, I was like, oh, I don't know even sure if I spoke to him. Your voice is a lot
Yeah.
deeper. I forget that sometimes.
Yeah.
All right. Well, feel free to contact me by text or email. Text is really better, especially now that I'm sick, because I don't know what the crap I'm going to be at any point in time. So,
Yeah.
by all means, do that, and just keep an eye out for emails, because I'll let you guys know when I'm finished with your exam and all that good stuff. Have you started taking your face-to-face redo test yet?
Yeah.
Okay, cool.
Yeah.
Good deal.
All right. Well, yep.
Have a good one, man. I appreciate
Yep.
it.
You too. Thank you.
You're
Feel
welcome.
better
Thank you.
too.
Appreciate that. Bye-bye.
Yeah. Bye.